This episode is brought to you by Chapman University. From climate science to patient safety, genomics to drug design, Chapman University data scientists are turning massive information sets into life-changing impact. The future is unfolding in Chapman's Schmid College of Science and Technology. Here, masters and PhD students join in cutting-edge research as they prepare to take the next big leap in their professional journey. To learn more about the innovative tools and collaborative approach that distinguish the Chapman program in Computational and Data Sciences, visit chapman.edu/datascience. That's chapman.edu/datascience. All right, let's do this. How are you, data scientists and engineers? How are you, business people? What's up, nerds? Did you grasp that thing you were studying? This is Data Science at Home, the podcast about machine learning, artificial intelligence, and more good stuff. I am Francesco. I'll be your host for the next 30 minutes, so grab a cup of coffee and join me as we learn more about the topics we love most. Welcome back indeed. I am very glad to start another episode about Rust. It's not a mystery anymore that I am so much in love with Rust and I'm trying to replace whenever I can all the Python based engines and code that I've written so far. Of course, when I have the time and when I have the opportunity and the particular use case, I always encourage myself into migrating into Rust, and so rewriting some of the code that I wrote in the years as a in this new language, which is definitely impressing me every day I use it. So, well, today we are going to speak about something that the folks of this episode definitely do on a daily basis, which is data manipulation. And by data manipulation, I mean probably the number one library that everybody's using out there, which is Pandas. And so Pandas is the, some kind of the de facto standard of data manipulation in the community, used by the industry, used by, in our personal projects. Pandas is the way to go when you want to, for example, import a CSV file, or you can even read directly from S3 bucket in Amazon or wherever your data, raw data is. You can import these things into an internal representation that is the representation of Pandas that is essentially putting stuff in memory. It exposes an API that is essentially a way to manipulate the internal representation of your data frame. And so you can start slicing things, you can start selecting records or rows, selecting columns, changing values, joining, merging, mutating stuff, grouping by, all this stuff. We know how it works. We know how comfortable Pandas is, and it is a very nice piece of software. I mean, I grew up on Pandas, and probably I hopefully will not die on Pandas because there are many other ways of doing the same things, and of course there is a little higher price to pay sometimes, but the results and the performance that you bring home can be really astonishing. And so today in this episode, I would like to make a direct comparison between Pandas and Rust, because there are some benchmarks and some source code that allows you to do exactly the same on exactly the same benchmark data. In particular, I will be referring to a data frame of 160,000 lines, so rows, and 130 columns. So it's a pretty large, though not very large, data frame of about 150 megabytes. This size has been chosen because there is a post that I'll definitely report in the show notes of this episode that it has really intrigued me about this direct performance evaluation between Pandas and Rust. And so I will try to draw some conclusion out of this experiment, what is good and when, and why you probably should or would like to spend a bit more time learning Rust or definitely getting closer to it. So what is Pandas? Pandas, as I said, is the de facto standard for reading and manipulating files or data in general. With this example, I will go with the CSV, which is probably the most common data format out there, though not the best in terms of efficiency or performance. It's not a binary, remember, so computers are much better with binary stuff than text. But anyway, the CSV is recognized format everywhere, and so let's go with that. Well, the first thing that you would like to do when, before manipulating data, of course, is loading data. This is something that we are all familiar with. The read CSV is one command from Pandas, no big deal there, one line of code, provide the path where the CSV file is, and you're good to go. What you have is the handle to a data frame, so-called Pandas data frame, that allows you to, start working on the manipulation part. When it comes to Rust, of course, there is much more code to write, though there are crates that already provide you, and it's an easy job. There is the CSV crate, which is very well written, though it's a bit more complex than the simple read CSV from Pandas, due to the fact that you are going low level here. So with Rust, if you haven't listened to the previous episodes on this show, Rust is a low level language, all right? It's not garbage collected. You have to take care of everything. If you want speed, if you want to drive a Ferrari, you have to know how the engine works. And especially if you want to push that Ferrari to its limit, you have to know how the internals of that car work, because you have to inform your engineers that something is not going well, or you can exploit some of the hardware capabilities of your Ferrari so that you can improve and increase the speed, right? So that's exactly the same concept with Rust. You are low level, you are right in front of your machine, like the hardware stuff, and so you can optimize your code as fast as your hardware allows. Rust and manipulating data can be kind of an overshoot. It was a few years ago. Now that these crates are out and they are becoming more and more mature, it's becoming, I'm not saying a piece of cake, but a less bitter pill to swallow. So there is this crate CSV reader. In the show notes of this episode, I will report all the links of the crates that I'm going to speak about. So you load your data, what you get is a file descriptor, and then the file descriptor is passed to this crate, and the crate returns a handle to, a bunch of memory. It's not really a data frame yet. It's just a chunk in memory where your data is, right? So that's what Rust leaves you. Now, what happens next is that you have to do something that essentially all computers do. Python too, they just don't tell you. They hide all that stuff behind one command, but don't think that, in Rust we are supposed to do more things than Python. It's exactly the same, in fact. What I'm talking about is the serializer, deserializer, that takes that chunk of memory / raw data and starts formatting these things into, these bytes into something more structured. For example, the 130 columns that we mentioned, and each column has its own data type. There are strings, there might be integers, floats, and so on and so forth, right? So that's exactly what the serializer, in fact the deserializer, does. Now in Rust there is a crate that I've been discussing about in another episode about the data model in Rust that heavily uses SERD, which stands for serializer deserializer. And that's probably one of the most used crates in the Rust community, or in the Rust ecosystem, in fact, because you serialize and deserialize stuff almost all the time when it comes to algorithms. So what SERD does is essentially unpacking or structuring all these, spaghetti bytes in memory into something more structured. And so what you have to do is definitely defining how would you like your bytes to look like. Right? And so, for example, I would like to look at my data frame in a much more ordered way, which is, in this case, 130 columns. Every column has its own type. And so I would like my data to be structured like that. Now, what you usually do with SERD is defining this schema, right, as a struct, which can be done manually if, for example, the number of columns is, approachable. If you have a dozen columns, still okay. If you have 100 columns, defining the fields of this structure, manually, it's gonna be time consuming, error prone operation. You don't want to do that. And so that's why there is another way to generate these things automatically. And so essentially parsing your records and generating the schema by parsing the records record by record, right? And so essentially what you want to do is scan your data and parsing values. If you find an integer, you generate a field that is of type integer. If you find a float, you just parse, and if the parsing succeeds, you generate a string that tells that in the schema there should be a float, and otherwise you generate a field that defines a string for that particular column. So in fact, you generate the schema in a very simplistic way, but it works. When you have a lot of columns, you can just scan your data and parse things and generate data types as you parse them, right? Now in Rust, there is one particular keyword that allows you to parse things optionally. So you might be parsing stuff that, it's an integer, but it could also be that there's nothing in there. And so, nothing is not an integer. So you want to parse something that is called option integer, right? And like in English, you say it's an optional. It's not strictly there, can be there. If it's there, it's an integer. If it's not there, it's probably an error. And that's exactly what you do in a scan. So complexity there, linear with the number of rows, O of n, where n is the number of rows. Still, everything is under control. Now, let's move to the next step. When you have your schema, you have deserialized your spaghetti bytes in memory, and you have everything. I should not call this spaghetti. I should just call it bytes, Some computer scientists out there might be offended if I keep saying spaghetti bytes, but you get my point. Something that is not structured and becomes structured because you enforce a schema on top of that, right? Okay, so the first operation I'm going to discuss is the filtering. So the filtering is what in Pandas we call it slicing, right? So you want to select, for example, a particular column of your data frame, and of that column you would like to select, for example, only certain values, right? And so you can slice your data frame and select only the rows where a certain column has a value, or selecting only certain columns, and so on and so forth. So it's a simple slicing. Now, to do this in Rust, of course, it is possible after you have deserialized your data. And what you do is something very, very similar to what you do with Python, just that, it's a change of syntax, of course, a bit more lines that you have to write. Nothing amazing here, and nothing amazingly different. But when it comes to performance, 160,000 records and 131 columns are processed with Pandas. Again, same slicing and same values. Pandas takes 3 seconds. Rust takes 1.6 seconds, so 50% speed up. So that's impressive already. We just changed language, and you are going low level. We are getting rid of the Python virtual machine. We are going straight to the memory and deserializing there and slicing. That's it. Memory usage. Pandas is quite inefficient when it comes to memory usage. It uses up to 2.5 gigabyte. Now the file is much, much smaller, but when you put things in memory, things start to blow up because, the internal representation depends pretty much on how the author of that library decided to represent that data internally. Not only that, much of the data is copied for several reasons that I'm not expanding on here. But long story short, Pandas requires 2.5 gigabyte of memory, while Rust requires 1.7 gigabyte. So it's another 30% of cutting the costs of memory usage, which is impressive. It's just one line of code in a different language and gives you already this improvement. Now, where things get relatively nasty is on other operations, for example, group by. So group by is one of those operations that are are very well known in the literature. There has been a lot of algorithms out there that have been designed for facilitating group by on the same machine, or having group by on in a decentralized fashion or distributed fashion. And that's where, you know, the smartest algorithm starts making a difference. But in this case, we're gonna refer to a standalone machine, probably one core, single-threaded application. So no big deal there. The comparison is really on bare metal, right? So in Pandas, when you want to group by, well, okay, the syntax of Pandas is amazingly short. You take the data frame, you call the group by, you define the column on which you want to group by, and then you provide also other columns where you are defining an aggregation. So you say, I want to group by column 1, and I want to sum column 2 and make an average on column 3 and report only the counts of column 4, right? So for all the other columns that are under the group by, you want to provide an aggregation method, right? And you can do this in 2 lines of code, maybe 1 if you are lucky, if you don't have a lot of columns to aggregate on. In Rust, this becomes a nightmare. So of course I cannot do code on a podcast, but believe me, in the show notes of this episode, you will find the code to these things I'm talking about. And when you compare Pandas group by and Rust group by, you're gonna be shocked. Because indeed the syntax of Rust for a group by, you know, and what you need to do to prepare that group by operation are really time consuming and definitely prone to error. And you probably, if you're not familiar with Rust syntax, you're probably gonna need a couple of hours to do this. But once you do these things, you know, these are patterns, right? These are operations that are very much recurrent in computer science, in all the algorithms that you write, be it a regular data frame manipulation, be it a database engine or whatever. A group by is a function that you would like to add to your arsenal, you know, code arsenal. And so next time you're gonna need a group by, of course, you don't have to re-implement it from scratch. You have it there, you change some parameters, you change column names and stuff like that, and you're good to go. So don't get frustrated when you see, you know, group by takes more than 20 lines of code in Rust and just 1 in Pandas, because these things can be reused, and that's exactly the purpose. But let's speak about performance. Pandas takes almost 3 seconds, 2.8 seconds. Rust takes 2 seconds. So there is a bit more than 30% improvement in terms of time. And as per the memory requirement or memory usage, we have exactly the same as before, 2.5 gigs for Pandas and 1.7 for Rust. This depends pretty much on how Pandas and Rust represent data frames, or well, data in this case, in memory. Okay, so that's just a way that the compiler decides how to align bytes in memory, and what Pandas, or well, the author of Pandas library decided to do. With that respect, we have, I would say, overall a 30% improvement both on time and memory requirement, memory usage. I think it's also very, very interesting. 30%, folks, is something that is already impressive in terms of performance. If you are dealing with production systems, observing a 5% or 10% improvement is already a big deal, especially when the system has been already kind of optimized. Having a speed up of 30% is impressive just by changing language. You're not changing architecture, you're not changing hardware, you're not changing platform. It's just a matter of hiring another developer. That's it. Now, where things become really, really interesting is on InPlace Editing. So when in Pandas when you want to change values in place, so you have your data frame, you perform a certain operation on each element of your data frame, and then you would like to write that result back to the same data frame, right? I believe this has happened to you a number of times already. And so you want to essentially use the same data frame as an input and an output at the same time, right? So InPlace is something that I personally try to avoid as much as I can, and also many of the big data engines out there try to avoid as much as they can, because when it comes to, for example, concurrency, InPlace editing can be dangerous because it can leave different parts of your code that access the same data in an inconsistent state, because, you know, depending on who reads first, and then you edit InPlace, and then, you know, the next owner of that particular data frame will read something that the other owners didn't read or haven't read yet. So, you know, you have to control these inconsistencies via you know, mutex or guards. We have to go into the discussion of concurrency and parallelism. That's not the day, but that's what we are used to do in Pandas. When you want to do this in Rust, again, there's a bit more code to write, not so much this time. I would say it's not a design pattern, but it's something that definitely can be reused over and over again like before. But when you hear about the performance, well, that's when things become really, really different now, because Pandas takes something like 13 seconds and Rust takes less than 2 seconds. So it's almost 90% speed up. 90% speed up. That's impressive. And when it comes to memory usage, Pandas requires almost 5 gigabytes and Rust requires almost 2 gigabytes. So it's more than 60% improvement or less memory usage for Rust. So this is, you know, something that is really interesting and really to keep an eye on. We all knew that Pandas do not scale for certain operations. In this particular experiment, we can see that Pandas cannot scale for example, line-by-line lambda functions that are not custom built. So in Pandas, there is a way to apply lambda function to each element of the data frame or the column. And when these lambda are primitives, usually these things are optimized because they've been implemented in, you know, they have a backend in C, and so it's fine. You know, you use Python just as a wrapper, as a language that calls a backend written probably in C. So on large data, you don't feel the difference because, you know, except for the initial time spent in using Python and using the Python bytecode and then calling the C implemented backend, that delay will be spread over the fact that the data is pretty large, and so you do that call once and you enjoy the speed of the C engine for the rest of your data. But in this case, we don't have a primitive function, we have a custom function. So the lambda that we are applying to each element is custom, is defined by the user, and which means that it's pure Python. Now, if you try to run pure Python code on each element of your data frame, on millions of cells, for example, well, then you are in danger because this is exactly where the performance is leaving you. And so that's why the difference here is massive. 13 seconds versus less than 2, 5 gigabytes of memory versus less than 2 is something that you really have to keep an eye on, because these are the type of numbers that allow you to, well, in fact, force you to think about Rust or a low-level implementation, especially when you are dealing with, for example, edge devices, very limited hardware devices, or even mobile phones, or devices that cannot dissipate too much energy or simply do not have so much memory, and you still would like to have those computations performed on the device rather than on a centralized server. So, you know, Rust is not only providing better performance, but in this particular case is allowing you to continue with your project or not. So these are the cases where, in my opinion, Rust is unbeatable, as C was when Java came out. There were problems that Java could not solve in many of these critical situations. The last operation I'm going to discuss today is the merge operation, so merging two data frames. Also, this is something that we have been doing in Pandas over and over again. You have two data frames, you define the column on the first data frame, a column on the second data frame, and you ask Pandas to merge them on the left column and the right column. So you want to merge the two data frames and have at the end a bigger data frame where the two common columns, or the columns you are merging on, become one, and that's the stitching part of the two data frames, right? How many times I've been doing this? Loads. Now, can we do that in Rust? Sure we can. Again, this is another nightmare because the amount of code that you have to write to perform this merge can be tough. To be honest with you, it took me some time to understand what that code was doing. So yes, it's definitely, I have to be honest here, it's very much time consuming. But again, in a fair comparison, we got very similar results to what we had for the InPlace editing. The usual performance: Pandas 23 seconds, Rust a bit less than 6 seconds, memory 12 gigabytes for Pandas versus 2.6 gigabyte for Rust. So again, 75% and 78% improvement on time and memory usage. So here you have to understand that, okay, at the beginning, if you are new to Rust, it's gonna take you a while to write that code. But as you get more and more familiar with Rust, you're supposed to take much less time developing these, patterns that are very recurrent in your projects, and you can reuse them over and over again. But the time that you spend to write low-level code in a, I would say, much tougher syntax than Python, it's time that you save while your algorithm is running, right? In this particular case, I'm not saying that you're writing code in 13 seconds, but that's what the speed up that you have on a simple 150,000 record file. Now, if you're dealing with millions of transactions, think about a bank, this can take hours, right? If you're trying to merge stuff that goes over the gigabyte in terms of disk space, well, this can take hours, or can just become prohibitive if instead of merging on two columns, you start merging on multiple columns, or instead of having an in-place replacement with a simple algebraic operation, you have a very nasty mathematical formula that takes a while to calculate, right? These are situations in which coding time can definitely be balanced back with execution time. Of course, you have to analyze your particular use case, and that's why, if I want to conclude this episode, I would say go with Pandas when it comes to relatively small data sets. So when you are below, for example, 500,000 lines or records, I would go with Pandas. I would not even think of using Rust or leveraging Rust power for such things, unless, of course, my project is written in Rust. It's natively designed with Rust in mind. All the other components are Rust. I'm obliged to. But that's another use case. That's the case in which you don't really have a choice in terms of language that you have to use. But in all other cases, when you are experimenting, there is a limit where you want to, use a rifle or a cannon. It depends on your particular, on the size of your data and the particular scenario. I would use Rust when I have really complex operations, when I have a lot of memory constraints, when I have functions that I have designed myself, they are not primitive functions, and especially when I want software that scales, which means that there are multiple owners accessing, for example, data, the same data, and so I might be running into race conditions, I might be running into locking mechanism that slow down my entire pipeline because there are multiple owners or multiple consumers of the data that I'm sharing across. So, there are these particular situations where Rust is designed for, and so that's a no-brainer. But in all other cases, I would say the right answer is always in the middle. I've seen already a number of times converting, loading data frames from Pandas, doing the transformations that you need to do, the stuff that Pandas is good at. For example, Pandas is good at MapReduce operations. And then store these intermediate representations after the transformation to disk or as an array or as a chunk of raw data. And then you load these things from Rust and you continue your pipeline with Rust. So you take kind of the best of both worlds. And so you you use Pandas as long as Pandas is performing, and then when it's time to switch, you make that switch. And the fact that Pandas is much more mature when it comes to, for example, loading different formats. Rust is not yet there. It will be there, I'm sure, but for the time being, of course, in the Rust community, there are many other priorities rather than, manipulating data the Pandas way. But of course, we are all welcome to contribute to the Rust ecosystem and provide some of the tools that we use on a daily basis. So that's something that I definitely would like to see. If I have some time, I would contribute myself, of course. And I will also provide in the show notes of this episode some of the tools that are more usable for a data scientist, for a machine learning practitioner. So there are some crates that are really interesting and to keep an eye on. So to conclude, when you change from a very well-known library like Pandas to Rust, you might be expecting speed ups that go from 2 times to 50 times improvement. And so that's something that, as I said before, is something that you have to really consider when it comes to projects that are living on the edge, so-called edge devices, for example, or minimal hardware and stuff like that. That's it for today. I hope you enjoyed the show. And of course, I would love to see you on our Discord channel. You will find the link in the show notes of this episode at the official website, datascienceathome.com. See you there.
You've been listening to Data Science at Home podcast. Be sure to subscribe on iTunes, Stitcher, or Podbean to get new fresh episodes. For more, please follow us on Instagram, Twitter, and Facebook, or visit our website at datascienceathome.com.